goal of having this local talk, I guess, is to give you a brief overview of some of the directions we have been pursuing over the last couple of years. And the topic will be on trying to get a better handle on quantum field theory using ideas from information theory. Now, why quantum field theory? Well, basically because it's a framework that describes quantum systems that have many degrees of freedom, and we get all sorts of interesting emergent behavior out of that. Okay, and one form of the problem would be given a particular microscopic QFT, understand its long-distance dynamics. This is in general pretty hard or impossible, but there is a kind of approximate but systematic approach which was suggested by Wilson, which is the renormalization group, which says that instead of trying to solve the full problem, you should think about trying to formulate the physics at the given scale lambda, described by an effective field theory. That effective field theory is obtained by integrating over degrees of freedom with energy above the scale you are interested in. And these theories at different scales are related to each other by a flow in the space of couplings. So the couplings start depending on energy as dictated by the beta function. So basically, Wilson taught us that instead of trying to think hard about a particular microscopic Hamiltonian, we should start thinking about the space of QFTs and the energy flows in that space and the structure of fixed points. Okay? And this is a cartoon I stole from the famous Wilson-Colbert review. So the property I want to focus on today is that over the years, there have been indications that these flows are in fact irreversible, something like the second law of thermodynamics. The intuition being that as you integrate over these high energy degrees of freedom, you are losing information. Okay? And perhaps the most famous example is this Samolov-Chaikovsky theorem that establishes the irreversibility in 2D CFTs and the flows there. Now, over the years, they have been accumulating more evidence about this. And here I'm listing some of the theorems that have appeared in different dimensions. So maybe the simplest one is the G theorem about irreversibility in systems with impurities. So 0 plus 1 quantum mechanical systems coupled to a conformal field theory. The C theorem I just described about 1 plus 1. More recently, the F theorem about the renormalization of the constant term in the entanglement entropy of a circle. The A theorem that was proved recently, and various hints from holography that suggest that, in fact, this C theorem should occur generically in any dimension. Okay? Now, when going over this list and trying to think about the problem, one realizes that extremely different tools are used to prove any of these theorems, and very different from each other in different dimensions. So it's clear we are missing the underlying principle that operates behind this irreversibility of the RG. And we should try to understand what that is in order to try to generalize these renormalization group theorems. In particular, it's important to come up with a concrete and also useful way of comparing QFTs at different energy scales, maybe by defining a distance in theory space. And as you can see from the list, in fact, from QFT, we have no clue about what happens beyond 4 dimensions. So it's a very important question. And I won't have anything to add about that, but what happens for D equals 5, 6, and so on. So in this talk, I'll give a brief review about progress in understanding some of these questions. And this is based on collaborations with people that are here in the audience, Horacio, Ignacio Salazar, and Eduardo Deste. And I'll roughly divide the talk in 2 parts. So in the first talk, I'll try to argue that this underlying principle that in order to understand the reversibility of the RG is related to the relative entropy and the relative entropy in the null limit. And in the second part of the talk, I'll be applying that to derive a single formula that works in 3 dimensions and that predicts all these known irreversibility theorems. Okay. So let me start from the first part. So we want to see how we can use quantum information theory to address some of these questions about the RG. So how is it that it's the natural framework to do that? And to that, we thought about starting with the simplest possible RG flow. It's kind of maybe a special starting point, but we actually got intuition from there, which is this boundary RG flow. So I'll describe briefly that for you. And the setup is we have a 2-dimensional CFT. The CFT has a boundary, say x1 equals 0. At first, the boundary preserves half of the conformal symmetries. This is what's called a boundary CFT. These boundary CFTs are characterized by a number G. This G is very intuitive. It essentially measures the number of degrees of freedom that are localized at the boundary. Okay? It's very physical because, for example, you can measure it just from the thermal entropy. You look at the thermal entropy, and there appears this constant term that characterizes this number G. And these appear very beautifully and importantly in the quantum model, where you have, say, magnetic spins in a gas of conducting electrons. And in that case, this G essentially measures the number of spins you have in each impurity. Now, there is a G theorem that says that this G decreases monotonically along boundary RG flows. What's a boundary RG flow? You basically take your boundary CFT and add a boundary perturbation, so some relevant operator localized at the boundary. That triggers a flow between a given boundary CFT in the UV, another boundary CFT in the IR, and Affleck and Ludwig, and then with the later proof by Friedan and Konecny, it was established that G in the UV is bigger than G in the IR. Okay? We want to understand this result using quantum information theory. Now, a first step for that was given by Cardy, who realized that, in fact, this G can be measured from the entanglement entropy. Okay, so the setup is the following. Again, we have the boundary, the half CFT, and you consider the reduced density matrix on this interval R, where the impurity is at the middle of, or if you want, this is the endpoint of the interval. And then Cardy showed that the entanglement, so the von Neumann entropy associated to this reduced density matrix has the standard CFT form, so the central charge times log R, but then this log G that was appearing in the thermal entropy also appears in entanglement entropy. Okay? So the idea is that if we want to understand differences between log G in the UV and log G in the IR, we should start thinking about differences in entanglement entropy between the UV CFT and the theory along the flow. So the question now becomes, what can we say about monotonicity properties of delta S? So not S, but delta S, so changes in entanglement entropy. And now this suggests thinking about the relative entropy. Why? Well, because delta S is a term in the relative entropy. Okay? So let me briefly remind this for you. So we'll be working with, throughout the talk, with two density matrices. I call sigma the vacuum, so the density matrix for the vacuum of the UV conformal field theory, and rho will be the density matrix associated to this theory that has the relevant perturbation. Now, both theories have the same operator content, but they just evolve with different actions. So we can think about comparing them, and we compare them using the relative entropy, which has this definition. So it's essentially a rho log rho minus rho log sigma. Now, this is a very important quantity in quantum information theory because it's related to many other quantities. It's essentially a measure of the distance between states. And recently, it has also had many interesting applications in physics that I'm not citing here, but I did want to mention that. And we introduced the modular Hamiltonian that was nicely described by Eric and other speakers also. So this H will be the modular Hamiltonian associated to the CFT. That's an important point. So it's log of the density matrix of the CFT. In terms of the CFT modular Hamiltonian, then the relative entropy essentially has a free energy interpretation. So it has this term delta H, which is a change in the expectation value of the modular Hamiltonian between the state sigma and the state rho. And then it has the term we are looking for, which is the difference in the entanglement entropy between the one from the CFT and the one for the theory along the RG flow. Okay, so this is the term we want to understand. So this is, in principle, looking promising because the reversibility of the RG that is measured by delta S could then be associated to the monotonicity and positivity properties that we know that the relative entropy has for general quantum systems.
So these are all ground states?
Yes. This is, both are the vacuum states for the theories. One is the vacuum state for the UV fixed point, and the other is the vacuum state for the theory along the RG flow. Now, as I was saying, this is looking nice, but the simple idea does not quite work because generically one finds that this term, delta H, is much bigger than delta S. And that would mask any potential monotonicity properties for delta S. Okay? So what we need to do to make progress is try to minimize the contribution from delta S. And the proposal to do that is to start thinking about quantizing the system in different Cauchy surfaces. So let me briefly describe that. So again, here we have the setup with the boundary and our interval R. So this has all this causal domain of dependence. So these are all the points that unitarily evolve into each other. So instead of thinking about the surface here at constant time, we could think about any other surface inside this causal diamond. And they are all connected by unitary evolution. Of course, the entropy doesn't change when you change the Cauchy surface, But the crucial point here, and it's a kind of a confusing or maybe subtle point, is that in fact delta H does change. And it does change because it's comparing states, rho and sigma, that evolve with a different evolution operator. And in fact, I'll be showing a couple of expressions showing explicitly the change in delta H. Now, recall that also as Eric was showing, for an interval, or more generally for a sphere, we have an explicit expression, a local expression for the modular Hamiltonian, because it's just associated to a symmetry. It's the conformal Killing vector that keeps the sphere fixed. So the modular Hamiltonian is just a contraction of that conserved current. So this psi is this conformal Killing vector. Here we have T mu nu. We simply need to contract that with the vector that is normal to the Cauchy surface that we are using. So we can understand that modular Hamiltonian either at constant time or any other time just by contracting this conserved current with the appropriate normal vector to the Cauchy surface. Okay. So maybe the familiar expression here is the static limit. So when we consider x0 equals 0, this line here, and then we get the expression that was shown in the previous talk also. Now, what can we say about delta H? Well, for that, we need to understand the change in the stress tensor between the two states. And the two theories are the same in the bulk, but they differ on the boundary because one has a relevant perturbation term on that boundary. And then one can argue that, in fact, the change in the stress tensor is just a delta function. It's proportional to a delta function localized here. So if you plug that delta function into this expression, you see that basically it gives an expression that goes like linear in R. So the Hamiltonian is growing with R, while the entropy has this subleading constant part. So this is extensive behavior. And essentially what's telling us is that the relative entropy is distinguishing the two states too much, and then it's not useful to derive monotonicity properties for delta S. But now, what happens as we take the null limit? So now we start thinking about these Cauchy surfaces that approach, say, this null direction here. I'm parameterizing this by null coordinates, x minus here and x plus here. This would be then x minus equals minus r. We can then very quickly write the modular Hamiltonian there. We just use the new normal vector. Then it has this expression. So it's now proportional to r squared minus x plus squared. Now, again, the effect in these null coordinates is located at x plus equals minus r. So the change in the stress tensor now is proportional to this delta function. But now you see that plugging this delta function into this expression, you get 0 because this prefactor vanishes. So as one takes the null limit, indeed, the contribution from the modular Hamiltonian goes to 0. So physically, what's happening is that as the null limit is taken, this impurity now sits in a region of higher and higher temperature. Right? And this was a contribution to the free energy or the relative entropy that goes like energy over temperature. So as you are increasing this local temperature, you are decreasing the contribution of the modular Hamiltonian to the relative entropy. And this will be an idea that we'll then use in the dimension. So taking the null limit is like taking a UV limit where the distinguishability between the two states is decreased. Now, then this is a nice result because the relative entropy is literally the difference between entanglement entropies. Now, remember this expression I gave before for the entanglement entropy. So both have the same CFT part, but then the two theories differ in the log G part. One has a G that is a constant, it's just the G in the UV, and then the other has a G that depends on the size of the interval. So the relative entropy is simply the difference between these two G functions. And now we can use the fact that the relative entropy is monotonic under increasing the interval, okay? Because you get more distinguishability, so this is positive, and then we get that G prime is less than 0. So in other words, we get an interpolating function, okay, that decreases along the flows and interpolates between, say, 0 and then G IR minus GOV, and that's the G theorem. Okay? Now, next we said, okay, let's try to get these ideas and extend now this, but to Lorentz invariant RG flows. So I want to consider RG flows in D dimensions, starting from a CFT in the UV and ending in some other CFT in the IR, and these flows are triggered by turning on some relevant perturbation. I'm calling this by an operator O, and the condition is that the dimension delta of O is less than space-time dimension, so it's a relevant deformation. And again, I'll be thinking about the vacuum density metric for the CFT in the UV, and I'll call it sigma, and the one associated to the theory along the flow will be called rho. Okay? So I want to compare both states using the relative entropy, and the idea will be to try to minimize the contribution from delta H. So here is a cartoon in 2 dimensions in this case. So we can think about different Cauchy surfaces and then taking the null limit. So now this is Lorentz invariant. There's no more, there's not an impurity. The RG flow is happening on all space-time. So in order to understand delta H, we need to understand the change in T mu nu, right? Because again, we are thinking about here spheres, say with some radius r, and we know that the Hamiltonian for a sphere is this expression I showed before. So we need to understand the contribution T mu nu that goes into the expression for the Hamiltonian and for the entropy. Now, T mu nu basically turns out to have two factors. One is a geometric factor and another is a QFT factor. So the geometric factor is maybe the easiest one to understand. Basically, we're saying the change in T mu nu has to depend on only local quantities associated to the Cauchy surface because it's a local operator. It has to be of rank 2 and it has to be traceless. Okay, so what can we do? The linear thing you can do is just put the normal vector to the Cauchy surface, so two normal vectors and then this combination of the metric to make it traceless. And there will be higher order terms, but they turn out to be suppressed by the microscopic cutoff. And then there is a prefactor that comes from QFT. This encodes all the quantum corrections associated to the RG flow. It's basically some function that will depend on this coupling lambda and the UV cutoff epsilon that we are using to do the calculations. For example, to leading order in conformal perturbation theory, it will go as lambda square, and then because this needs to have dimension d, you can fix up the dimensions of the cutoff there. Okay. Now, plugging this expression for the change in T mu nu into the expression for the modular Hamiltonian for the sphere, you get this nice geometrical result that says that basically the change in the modular Hamiltonian is proportional to the contraction between the normal vector and this conformal killing vector associated to the sphere. In other words, it's just measuring the flux of the conformal killing vector across the Cauchy surface. Now, this is very promising because in the Lund limit, these two vectors are orthogonal, and then you get 0. So again, the contribution from the modular Hamiltonian would vanish. But here, we chose to be a little bit more conservative because this QFT prefactor could be divergent. Okay, because there is, for example, here for a dimension bigger than d over 2, this would diverge. So we say, let's be conservative. Let's say that we can approach the null limit only up to some size of order the cutoff. Okay, and if you do that, you get the following. So first, let me remind you what's the answer at constant time. So at constant time, the change in the modular Hamiltonian goes as the radius of the sphere to the number of space-time dimensions. So that's the super extensive behavior that we are used to seeing. So it's like energy divided by temperature, okay? But then as you take the null limit with this conservative assumption that you cannot approach the null limit closer than the lattice cutoff you are using, instead of this r to the d, you get an r to the d minus 2. So you go from this super extensive behavior, in fact, to an area law for the modular Hamiltonian. And that's important because then the modular Hamiltonian becomes of the same order as the entanglement entropy, and in fact, it can be made smaller. Okay? And in particular, notice that if this RG flow is caused by an operator of dimension delta, which is less than d plus 2 over 2, in fact, the QFT prefactor is under control, and then just the change in the modular Hamiltonian vanishes. Okay, so let me say what are the consequences of that. Okay, so in this case, the modular Hamiltonian vanishes, and then the expression for the relative entropy, again, is a change in entanglement entropy. So in d equals 2, then the relative entropy is just proportional to the usual log r, and then also proportional to the difference between the central charge in the UV and the central charge in the IR. And then positivity of the relative entropy implies that this has to be bigger than 0, and that's the sixth theorem, now as seen from the relative entropy. In d bigger than 2, there is something similar, but instead of the log r, you get an expression for the area terms in entanglement entropy. It basically says that the area term in the UV has to be bigger than the area term in the IR. Okay? And that's also interesting for connections with gravity because the area term basically measures the QFT contribution to the renormalization of Newton's constant. So, okay, so what are the lessons so far? So I have tried to argue that we should think about the relative entropy and then take the Lycon limit because this provides a useful notion of statistical distance between QFTs, okay? And it gives us the quantum information meaning of both G, C, and the area term, okay? It's basically saying that all these quantities are a measure of distinguishability between states. And then the irreversibility of the RG in this quantum information context is a measure of distinguishability, or if you want equivalently, a measure of how much information the IR state is losing compared to the UV state. Okay, so now I'll take the final step in the talk. I want to extend this to try to access other irreversibility quantities. In particular, I want to prove the A theorem in 4 dimensions, which we do know an entropic proof. So let me remind you that for conformal field theories in d dimensions, we can look at the entanglement entropy on a sphere of radius r, and it has this expansion. So it has some area terms, some subleading terms, and then in even dimensions it has this famous log term, and in odd dimensions it has a constant term. Okay? Now, in order to establish the irreversibility of the RG, we want to derive inequalities for the changes in A and F. But you see that from our previous approach, we cannot access that because we only had, at our approach, a first derivative of the relative entropy. If we want to access this quantity, we actually need higher derivatives of the relative entropy that would give us inequalities for high derivatives of delta S. And out of that, we could manage to prove A, F theorems in high dimensions. Okay? So then in order to get higher derivatives, we need to look at multiple regions, and in particular, the strong subadditive inequality. So now I'll argue in two steps. In the first step, I'll argue that for a conformal field theory, and for regions whose boundary is on a light cone, or on the null plane, then the strong subadditive inequality is in fact saturated. And this is the so-called Markov property. So the entanglement entropy for region A plus region B is equal to the entanglement entropy for the intersection and the union. And then given that for the theory along the RG flow, the strong subadditive inequality is non-trivial, then we find the strong subadditive inequality now for delta S, right? Because we can just subtract this, which is 0, out of the strong subadditive inequality for the theory rho under the RG flow. Okay? And then an intermediate important result will be this strong subadditive inequality now for delta S instead of S. And in the second part, I'll then argue how to use this to obtain the A theorem and some new theorem for gravitational corrections in high dimensions. Okay, so let me argue for this. So I'll actually first focus on the null plane, and then since we have a CFT, we can map it to the light cone. But in the null plane, it's slightly easier. So basically, this is the setup. I'll be thinking about some null plane with a coordinate x plus, so the normal coordinate will be x minus, and then all the other d minus 2 transverse coordinates are denoted by y. Okay? And then we'll consider regions A and B, which are here, and they are described by some arbitrary curve on this null plane. I'll denote this curve by gamma of y. So for example, here is x plus is given by some curve gamma of y. So these regions are all characterized by curves like this, and the entropy depends only on geometric properties of the curve. Okay, I'll then map this to the cone, and then this will be regions whose boundary is lying on the light cone. So here's a quick argument. So the entropy S has to be a function of gamma, so the boundary of the region, but it should be invariant under boosts because we are in Lorentz invariant QFTs. Now a boost on this null direction just acts by like a dilatation. It's multiplying x plus by a factor lambda. So we can simply do a boost and then take lambda to 0. What that will do is it will take this arbitrary curve and shrink it to a line, right? Because then it's just shrinking everything by a factor that goes to 0. So this means that the entropy, in fact, has to be independent of the curve. So for any region with any curve, you get the same answer. So the entropy has to be independent of the curve. And then saturation of strong subadditivity follows immediately, because once the entropy is independent of the curve, then these terms just cancel out point by point. Okay, so that's a quick argument. So there is, in fact, a stronger property than the saturation of Markov, that is that the entropy is independent of the curve. Now, this is actually true for any QFT. Okay? But if we are thinking about CFTs, then we can map this Rindler setup to the light cone. Okay? We just do a conformal map, as was also reviewed before today. Okay, so here we have the setup, we have the light cone. Now the curves here is described by, say, this R minus or R minus t, so the radial direction minus t, given by some curve gamma, which now depends on the angular direction from the cone. Now the previous result that the entropy is independent of the curve means that on this side, the entropy, all the dependence on the curve can only come from the fact that we have a cutoff. Okay? Now, because it's cutoff dependence and we have a local QFT, it has to be local and extensive. Okay? And in fact, and moreover, the possible terms that enter here can be classified using the fact that we have Lorentz invariance at our disposal. So this means that the entropy now on this cone can only be a local integral over these angular directions of some function that depends on the curve and the cutoff. Okay? And here, just for illustration, I'm showing what would be this expression for the entropy of any curve gamma in d equals 4, so it will have this term. Then this is the term associated to the anomaly and so on. So it turns out, in fact, we can write all the expressions for these entropies on the light cone. Okay? But then, now, for us, the important point will be that once we have this local integral, then ray by ray, all the terms in the strong subadditive inequality cancel out. And then again, we get saturation of strong subadditivity on the cone side. Now, I'll briefly make contact with this Markov property and start a different perspective. So one can, in fact, prove that saturation of strong subadditivity is equivalent to this operator equality, okay, that relates the density matrix in the union to the density matrix in the subsystems. So this one can be exactly reconstructed out of this combination. A state that satisfies this property is called a quantum Markov state because there is an analog property in classical Markov chains. Okay? And essentially what this is telling us is that tracing out over a subsystem becomes a reversible process, unlike what happens in a general QFT where it's an irreversible process. Roughly speaking, it's saying that there is no entanglement between different null lines when we think about CFTs. And in fact, the Markov property also follows from another stronger property, which is this result for the modular Hamiltonian. Okay? Here I'm just showing it for this Rindel setup, but it can also be written for the cone, which basically says that it's a local integral over transverse directions, and then it has this null integral, which is essentially the Rindler type of modular Hamiltonian. So basically, line by line, we get the Rindler expression, and all the dependence on the curve comes from this gamma of y. So this result is kind of striking because generically the modular Hamiltonian is very non-local for arbitrary shapes. But if that boundary lies completely on the null plane, then it becomes a local operator. Once it's a local operator, then this equality between modular Hamiltonians follows automatically. Now, this is the last part of my talk. So now I want to use the result to establish the RG irreversibility in d dimensions by deriving a formula that will contain all these partial results. And for this, we are using the geometric setup that was invented by Horacio and Marina around 2012 when they proved the F theorem from a QFT point of view. And there, remember, they basically considered this light cone, and then they thought about all these n-boosted spheres on the light cone, and they took intersections and unions to consider the strong subadditive inequality. Now, the intersections and unions of these spheres give wiggly spheres, but what stopped people from generalizing their approach is that, unlike what happens in d equals 3, if you think about this geometry in d bigger than 3, actually the entropy of these wiggly spheres does not converge to the entropy of regular spheres in the limit when the number of these wiggles goes to infinity for the strong subadditive. So that was a problem because then you get some strong subadditive inequality where you have spheres on one side, but then wiggly spheres on the other side, and you cannot derive anything useful. Now, our approach was actually using the Markov property in a key way because instead of thinking about strong subadditivity for S, we are now thinking about strong subadditivity for delta S, right? Which is something we proved because the CFT vacuum was saturating the strong subadditivity. Okay? And now, what happens for delta S, which does not happen for S, is that when the number of wigglies goes to infinity, all the differences in delta S between a wiggly sphere and a regular sphere is just purely UV, right? Because now we are thinking about differences in entropy and not just the entropy itself. Okay? This means that inside the strong subadditive formula, we can smoothly replace the contributions from wiggly spheres by contributions of regular spheres. So all the differences are purely UV, but because they are UV, they are vanishing in taking delta S, okay, inside this strong subadditive formula. And then their approach can just be copied and applied in 3 dimensions, but now for delta S. And essentially, so you get some strong subadditive inequality by applying many, many times these intersections and unions of spheres. That can be written as some integral of differences now in entropies of radius r with some density of spheres. And in the limit, when this boost goes to 0, basically this gives a differential equation, second-order differential equation, which is the result I'm writing here. So it's a second-order differential equation for delta S, which is the main formula we want to use to understand the irreversibility. Okay? And so let me now very briefly recall how this formula reproduces all the known irreversibility theorems. So here I'm just copying again this expression for the entropy for CFT. So we'll just plug these expressions for the UV and the IR into this formula and see what the formula gives in different dimensions. Okay? I'm almost done. This last slide. So in d equals 2, it basically says that this combination delta C defined as R times the first derivative in delta S decreases monotonically. And this is a quantity that is 0 in the UV, and in the IR, it measures the difference between central charges. Okay, so in d equals 2, we get the C theorem and a monotonic interpolating function. In d equals 3, something similar happens. You can define this combination, which is r times the first derivative of delta s minus delta s, and then this equation implies that delta f is less than 0. Okay? And it interpolates again between 0 and the change in this constant term f. So again, you get the f theorem and an interpolating function. In d equals 4, in fact, you get something slightly weaker. So we are starting to lose power as we increase dimension. So in d equals 4, basically, by plugging this expression there, you get that this combination of second derivatives for the entanglement entropy of the theory along the flow is bounded by the A anomaly in the UV. Okay? And now if you look at the left-hand side in the limit when r is large, the left-hand side is dominated by the logarithmic term, so you get that AIR is less than AUV. And this is the entropic theorem we wanted to prove. Okay? You do not get an interpolating function. And then in general dimensions, this equation gives two inequalities. One of the inequalities you can check is just saying that the area term decreases. This is something that we also proved before. This is in the relative entropy. And there is a new inequality. There is a new inequality coming from here, which says that the next subleading term to the area term, this mu that multiplies r to the d minus 4, increases between the UV and the AR. So this is telling something about the normalization of gravitational terms like QFT that we still don't know, but I think it's interesting to explore. It's probably something about R-squared corrections. Okay, so let me, I'll just end here. So I'll very briefly mention some work in progress we're thinking about. So I'll just advertise a little bit that the expression, the arguments I was giving for the independence of the entropy on the curve actually also apply to all Rényi entropies. So it seems all Rényi entropies for CFT actually saturate the strong superlative inequality. So that's much stronger than Markov. It's essentially saying that for the CFT vacuum behaves as a product state over the null cone. Okay? It's also possible to write down expressions for entropies in CFT with arbitrary curves, so they can be characterized from the QFT point of view. And we are currently thinking about consequences of this, so what can we use this for? Now you see, another, I think, an important direction for the future and something that was left open is how about C-theorems in high dimension? So we need inequalities for more regions, and we don't know them from quantum information theory. Or maybe some of you know them, and then you should tell us, or prove the theorem. We also were not able to derive a monotonic function in d equals 4. That would be important to derive. And more generally, I wanted to say that over the last year or so, there have been many applications of this idea that the entanglement structure simplifies dramatically over the light cone. For example, we have seen proof of the QNEC, so the quantum energy condition, generalized second law, monotones on the RG, and so on. So I think this would be a very fruitful direction to continue thinking about. Okay, thank you very much.
Okay, questions? I'll start with Dan.
So you had this sort of area monotonicity results
Yes.
about the area term.
Yeah, there are two of, this one and that one. Yeah, so
Yes.
the area term is monotonic, and then also a subleading term is monotonic.
Yeah, so let's say for the area term,
Yeah.
so in gravity, we think that the full entropy is independent of the cutoff scale. So then it seems like this might make a prediction about the sign of the renormalization of Newton constant.
Yeah,
But
exactly.
I thought actually the sign can go either way, depending on what kind of matter fields there are. So I don't know. Yeah, can you comment on that?
No, because, well, I mean, okay, so it's important that here we are, maybe I show it here where so it's this.
Yeah, that thing.
Exactly. So what this is saying, here we are measuring changes in the normalization of the Newton constant. So take some bare Newton constant in the UV for a CFT, and then apply energy flow, ask what's the change. That change has a definite sign. But I cannot tell you what a CFT does directly to gravity, because that's indeed a scheme-dependent question. But that's not what I'm answering. I'm answering what's the change. So if somebody tells you...
This is the thing that gets canceled by the renormalization of G Newton, right?
Yeah, sorry?
This gets canceled by the renormalization of G Newton.
Or you can...
You describe with the UV CFT.
Right, or you can just view it as, given some bare value in the UV, so what's the physical renormalized value of the Newton constant? You get it by adding this contribution. And this is the thing that has a definite sign. But indeed, if you just start from some QFT, then you can use different cutoffs and you'll get different signs. That's just saying that maybe either it's not the right, appropriately geometric cutoff, or you're not asking the right question. But this change does have a definite sign.
Yeah, what's apparently, yeah.
Yeah, right. Yeah, it can be proven in other ways, so the Adler-C formula and so on, but yeah.
So if I have a quantum field theory,
Yes.
and I'm looking at a null cone, do we have any arguments to this effect that there exists no states in the Hilbert space, that's Markov?
Can you repeat the question again?
If I have a quantum field theory that's not a CFD, and I'm looking at the causal, at the null cone,
Yes.
do we know that for a fact that there are no Markov states?
For a QFT,
For QFT.
I don't know. Here, we
So
could
for
only
vacuum-
establish that for a CFT. Yeah, for a QFT, I don't know. I would say, generically, it's not going to be Markov.
For sure, but I'm
Yeah,
wondering
that
if
I don't, yeah. I think, so if you take the setup where you start from a CFT and perturb it by a relevant operator, I think the answer will be no. Because, this,
Well, it will, yeah.
yeah, but, yeah.
Are the-
Even in the CFT, you were referring to the vacuum state, right?
Yes.
The non-vacuum state.
Can-
Not the vacuum state, you don't have to.
Yeah, all the statements here were for the vacuum state. Yeah. For example, if you consider a thermal state, it's no longer true that this Markov property holds. Yeah.
Are there any last questions? If not, the bus left 10 minutes ago. So perhaps we should thank all of this afternoon's speakers one more time.